and today we will be going over static failure, and more importantly, how we use Mohr circle to determine certain stress failures and things like that. And we can use those to determine safety factors around loads on beams, rods, pretty much anything like that. So what is Mohr circle? Very basic here. Draw it up. So you're gonna obviously have a plane. We're dealing with a two-dimensional case, and on this plane you're gonna have a circle of some point, and you're gonna need 2 points, typically 180 degrees apart, to determine how big the circle's gonna be, radiuses, and the stresses. You're gonna have tensile stress on the x-axis and shear stress on the y-axis. The max shear stress being located where the circle crosses the y-axis, and max tensile being where the circle crosses on the x-axis. These are your principal stresses, typically here and here. And this, we're going to use diagrams such as, we're going to have a square, we're going to have, y and x, y and x, and we're going to apply forces to that, tension, compression forces, something like this. And we even have a torsion, something like those arrows. And we're going to be able to calculate based on numbers provided the stresses in each plane. So let's get very basic examples of some of these. Okay, so let's say we just have straight up compression. So if we have something like that, our Mohr circle will look as so. It's going to be that's a negative x. Hopefully it's a negative. With the camera, it could be flipped and it could look positive here, but I drew it on the negative side. And your 2 main points are going to be the origin and that point right there, farthest end. And we're going to be basing this off of max tensile stress. Now, if we have tension, and of course these can be any way we want. So if we didn't want it in the y, we could have tension in the x too, like such. And you might be able to guess it, but then your Mohr circle will be in the positive side of the graph. And the last basic one we have is something like torsion, which will apply shear. And in the case of shear, we're going to be focusing on the y-axis in this case. I drew out the points there so you can actually see it. And it's going to, basic torsion is going to look like that. Now the thing is, we can also have a Mohr circle that ends up just being a dot. And when we have equal forces in the x and y in the same direction. So same compression example, but now if we were to add that and they all equal, let's go with the basic number, they all equal 5. Oh, sorry. Then literally we'll just have a dot. Oh, well, it'd be negative. So compression, you just have a dot like that. Same thing for tension. Okay, so now let's do a real example of how we can apply Mohr circle. Just gonna try this out real quick. So in this case, we are going to have tension in each direction, but we are only going to have, it's not all going to be the same, so they're not going to cancel out. So in this case, we have 30 MPa in the X direction, 50 MPa in the Y direction, and then we have a shear of 25. So the first thing you want to do is calculate your tensile average, which would pretty simple just be 50 plus 30 all over 2, which would end up equaling 40. So what we're going to do with that is going to be the center point of our graph, of our Mohr circle. So just put a point down there, it'll be your center point. Now what we're going to want to find next is the radius, so we can put on 2 more points on this. We're going to go with the x-axis because it's the simplest, just read out, then we don't have to do any weird triangle calculations. So how do we find the radius? The radius is going to be equal to the square root of your x tensile value, which in this case is 30, minus 50 all over 2, minus 50, which is your y. So your x minus your y over 2, and then you square that. And then if you have torsion or something, a shear, then you're going to do plus 25 squared. So it's going to look like that. Y, or x minus y over 2 squared plus your torsion shear squared. And that's going to give us a radius of 26.93. So now we're able to just add 26, pretty simple, into x. That'd be 6, so your max would be 66.93, and your minimum value would be, what's that? 13.07. So draw that on the graph real quick. And we can draw a pretty rough circle here. Bam. So we had the 13 and the 66. Oh, 13.07 and 66.93. So those are basics, and then also 2 other points we will know right off the bat, which I'm just gonna draw the dot on. Usually something like this is 50 negative 30. And 30, oh, negative 25. So we have 30, 25 here, because that's just a simple value you get off using your x and your shear. And we know 50 negative 25 is 180 degrees apart, and typically on a Mohr circle you have correlating points always 180 degrees apart. Okay, so next what we're going to use to start actually applying this to something like safety factors and stresses, more stresses, is we're going to need to calculate a R1. Okay. So let me erase some of this work. I'm also just going to get rid of the initial shear diagram. I hope I just wrote that down already. If not, go back. So we'll be calculating our tensile 1. No, not that. Tensile 1. And that is going to be equal to your average plus your shear, square root of 2, do the triangles. It's going to look something like that. That's the equation you're going to use. And in this case, when we plug everything in, 40, 25, we're gonna end up getting 37.67. That's MPa. And why do we need this? Well, we need this to calculate our max shear, so something, it's going to be this point up here, or down here, since it's symmetric along the x-axis. So that is equal to just theta 1 over 2. So in this case, it would be 37.67 divided by 2, 18.835, which doesn't make any sense. Okay. Let me redo one of these calculations. I see what I did wrong. It's 25 times square root 2. Okay, so our 1, I messed that up. No, over 2. I was skipping a step. I was going to our Tmax right away and putting in the 2. So our theta 1 is actually equal to 75.35. And our Tmax would be that divided by 2, which would be 37.67, which makes sense because 37.67 is definitely higher than 25, 18 wasn't. That's my bad. Okay. And of course, it would also be negative 37.67 down here at that point. So now on to the calculations for actual safety factors. So for this, we're going to be using pretty much all of our points here. So you have our tensile on the x squared minus the tensile on the x times the tensile on the y plus the tensile on the y squared plus 3 times the shear squared. Lots of squares, lots of stuff. Okay, so I'll plug that in real quick. So we got, what we get? We had 30 in the x, so 30 squared minus 30 times 50 plus 50 squared plus 3 times 25 squared, something like that we'll get. And that would end up giving us 61.441 MPa. And this is our von Mises criteria. So this is one of the 2 ways we can calculate safety factors. We got the von Mises and we got the distortion energy. So using that value, our first safety factor, and I didn't give us a maximum yield. So right now, I'm just gonna plug in our SY equals 200 MPa. Right there. Because our safety factor equation is SY over that value we just calculated, von Mises. And in this case, 200 divided by 61.441 would give us approximately 3.25 for our safety factor. I'd say it's pretty good. Now, if we were to base this off of distortion energy, we'd have SY over 2 divided by Tmax, which we calculated earlier to be 75.3553. So then we'd have 100 divided by 75.35. So our safety factor in this case would be 1.32, not as good. So this is going to be where we fail. Okay, and so you can pretty much do this for any beam, rod, anything you know the loading on. You can calculate, you can make a, let me not put that way. You can end up making a diagram using these forces and the the tension forces, the compression forces, and the shear forces, and the X and Y. Use those to build your square of some sort.